Hi, all, and welcome to Chapter 3, all about water, which we just got a little bit of an introduction to as we were looking at bonding in Chapter 2. So, why devote an entire chapter to water? It's not a long one, but it's its own chapter. And the reason is that the properties of water make life possible on Earth as we know it. If you think about it, water is the only common substance that exists in all three physical states of matter, right? It exists as a liquid, it exists as a solid, and it exists as a gas on planet Earth. It's pretty amazing. And the structure of the water molecule allows it to interact with other water molecules and with many, many, many other molecules, as we'll see a few examples of in this chapter. So, if you've listened to chapter two's lectures recently, then you remember this. If not, just briefly. Um, the electronegativity of the oxygen atom is such that it actually draws the electrons that it shares in these polar covalent bonds with the hydrogen atoms closer up to itself, right? So the electron cloud is denser around the oxygen atom than it is around the hydrogen atom, which makes the hydrogen atoms have a partially positive charge. Each one of them has a partially positive charge, and it makes the oxygen atom have partially negative charge. Now, the reason that you see these two areas here is because they're showing you these regions of real negative charge also around the orbitals that are paired with electrons here. Right, so these would be its own electrons that are in the shell, right, the outermost shell, and these are the ones that these are the two that it shares with this hydrogen atom, and these are the two that it shares with this hydrogen atom. So they conventionally put a partial negative charge around each of those two pairs up there. But overall, we have the electrons swirling up around the oxygen atom, pulled away from the hydrogen atoms, and making those hydrogen atoms um, have some partial positive charge, right? So we can say that the overall charge on a water molecule is unevenly distributed, right? With more negativity up around the oxygen atom and therefore more positivity down by the hydrogen atoms. And we know that each hydrogen is connected to the oxygen atom by a polar covalent bond, a bond that is not an even sharing of electrons. And that's what these red arrows are trying to tell you, is that the electron pair is found closer to the oxygen. But we know that they're not like that on a bar, that they're whizzing around, but they whiz around the oxygen more than they do around the hydrogen, right? So in that bond, you see them pulled up this way. And in this bond, you'd see them pulled up this way. Okay, so water molecules, therefore, are polar. They have a separation of charge, right, with a more positive end and a more negative end, right, or negative region, if you don't want to call it an end, and more positive regions. So the shape of a single water molecule, as you can see here, is governed by the geometry of its bonds, and that bond angle is always the same. And it can tell you that the bond angle is determined by the electrical repulsion that occurs, right? Because you have all of these negatively charged electrons, right? And so the four pairs, where's the four pair? Here's one, here's two, here's three, here's four, that are all in the outermost shell, right? They repel one another, right? So they try to get as far apart as from one another because in electricity, like dislikes like, right? So two negative charges repel each other. So the regions that have electrons try to spread out as far apart from one another, and that's why you get the bond angles that you do. In molecules. Okay, but because of the polarity, right? And now we have a more simplified model here where you're just looking at a partial negative on the oxygen and a partial positive on this hydrogen. They don't show you the rest of the charges on either of the two molecules. That allows for an electrostatic attraction, which is called a hydrogen bond, right? Because it involves a hydrogen atom, if you remember, bonded to an electronegative atom that is also made electronegative more by its own bonding, right? So this could be oxygen, because we're talking about two water molecules, it's always going to be between an hydrogen atom and an oxygen atom of another water molecule, right? Two different water molecules. This hydrogen atom does not, if you look at my cursor, this particular hydrogen atom is covalently bonded to this oxygen atom. It's a polar covalent bond, this solid line here. So you wouldn't have a hydrogen atom and an oxygen atom of the same water molecule doing anything other than having a polar covalent bond here. But the hydrogen atom of one water molecule can interact with the oxygen atom of another water molecule by this hydrogen bond, right, which is based on opposite charges attracting each other. Not full charges, these are partial charges. So this hydrogen is partially positive, this oxygen has partially negative regions, right? And the reason that this oxygen got this partially negative is because it's bound to something and taking the lion's share. It's bound to something that's not very electronegative, that's the hydrogen, and so it draws the electrons of that pair up around itself. And of course, the reason this hydrogen has the partial positive charge is because the electrons it's sharing with the oxygen atom have been drawn up towards the oxygen, right? It's just what you're seeing here. So the polarity of each water molecule allows them to make multiple hydrogen bonds, right? So we graduated from looking at two water molecules, and you have to know that each individual water molecule like this can make multiple hydrogen bonds with other surrounding water molecules. And that's what you see here. You see a water molecule making a series, if you look at the central one, right, making a series of hydrogen bonds with a series of water molecules that are surrounding it. And remember that the hydrogen bond is often depicted as a dotted line. So all of these are dotted lines. And in this example, they're trying to show you the polarity of each region, right? But you know it because you can see it up here, and so you could follow it down there. So there's quite the network of water molecules hydrogen bonding with other water molecules. And these hydrogen bonds give water tremendous abilities, as we're going to look at in this chapter. Okay, so we'll look at basically, because your chapter likes to look at these mainly, four of water's properties that are very helpful to Earth being suitable for life. So we're going to be looking at first cohesive behavior, then we're going to look at how water expands upon freezing. This leads to, ice floating, the ability for a body of water to moderate temperature. That's pretty impressive. And its versatility as a solvent, which is, slightly important to, let's say, our bodies. So these are what we'll focus on. So you'll see this slide a couple times. Okay, so I'm just trying to now sort of complicate the picture a little bit more or make it, more real. So you can see that these are all water molecules. And in this diagram, each water molecule is making multiple hydrogen bonds with other water molecules. And that's depicted by the dotted lines with the yellow highlight over it. So anywhere that you see a solid line, then that's a polar covalent bond, and that's part of the same water molecule. So the dotted lines are the ones that are the hydrogen bonds. But I bring this up because I want you to know that in liquid water, right, so the individual water molecules are very, very free to move about, that says. So hydrogen bonds are constantly breaking and forming. Right? So look at this. Chemists estimate that this occurs 1 trillion times a minute for a single water molecule. So everything's under constant motion, kinetic energy, right? These water molecules have kinetic energy, and they're constantly making and breaking hydrogen bonds. I mean, that's just such a large number. It's really difficult to wrap your head around it. But I wanted you to think this is not a slow process. So these are not long-lived bonds. Each individual hydrogen bond we learned in chapter 2 is not strong. It's also not long-lived. So these are constantly making and breaking hydrogen bonds. But that there is strength in numbers, even overall, because so many hydrogen bonds are at any one instant in time existing. Okay, so let's talk about the cohesion of water molecules, which is strength, right? So collectively, hydrogen bonds hold water molecules together, and we call this cohesion. So all the hydrogen bonding between all the water molecules, no other molecules but water are involved. This is called cohesion. Now, sometimes, as I showed you in chapter 2, I like to give you a second definition in case the one in green works better with how you want to think about it than the one in blue. So here's another one. Cohesion, the capacity of water molecules to resist coming apart from one another when they're placed under tension. Right. So if you want to try to pull it apart from one another, the water molecules have an inherent capacity to hold on to one another because of all the hydrogen bonding. Right. So in liquid, water molecules that are hydrogen bonded to one another, which they are, have what we call cohesive strength. And I'm going to show you that in just a moment. Adhesion, I have it de-highlighted. Is that a word? De-highlighted? I'll come up with it later. I have this, see, I guess I have to move on. It's driving me crazy. Okay, I will come back to it. I just don't have it highlighted at this point because we're going to move on to adhesion in just one moment. Let's look at cohesion first. So cohesion is so hydrogen bonding between water molecules, like giving it an ability to resist being pulled apart, is responsible for something that we call surface tension. And surface tension, this is a good definition of this, is a measure of how difficult it is to break the surface of a liquid. Right? So water has an unusually high surface tension due to all the hydrogen bonding that's going on between the water molecules at the air-water interface, right? And between the water molecules with each other and to the ones below. So I drew a beaker here. Well, I took a picture of a beaker and then I drew this little thing on top of it to show you. So this would be right here. Let me get out my draw tool. This obviously is the air water interface. So what it's saying is that the water molecules, I know you want to you want to watch this. Not. Okay, I'm going to pause this and then draw a few. Okay, I'm not even going to admit how long this took me to draw these molecules. Okay, so I'm just trying to make it clear. I don't know that this will, but the idea is that there are no water molecules for these water molecules that are at the very surface. There's no water molecules above. So the water molecules that are at the surface will hydrogen bond. Of course, they're not this far away, but I'm trying to show you regions with water molecules that are lateral and water molecules that are below, right? So, right, so an oxygen to and this one can go here, and this one can go here, and you can have this, right? So maybe this helps a little bit, I don't know, right? The idea that the water molecules at the surface are bonded all to one another right at the surface and to the ones below. So it creates almost like an elastic film at the top. So this is called surface tension. And if we go back to this slide, we can see that there are insects that have evolved to be able to use this surface tension and sit on it, walk on it, mate on it, do all those things. So I have a great little video that I looked at. So hold on one moment. Okay, so this is from the BBC and it's narrated by Richard Hammond. So if you've ever watched Top Gear or Grand Tour, he's one of the three that are involved in testing out all the cars and stuff. If you have a motor enthusiast at home, as I do. You will know him from that, but he also did a bunch of videos for the BBC early on for Invisible World. So watch. Okay, I hope you found that super beautiful. The BBC just knows how to do it. I mean, if you ever watched any of those nature shows, you know, most of the time you're watching and your mouth is wide open as you see these most amazing things. Maybe it's a perfect time to stop now because I'm going to talk to you next about cohesion and introduce adhesion as it relates to water movement in a tree, going up to from the roots to the shoots. So I'll stop and I'll start part 2 with that.